So thank you very much for having me here. And so I'd like to thank everybody here, especially Hakan, took care of us wonderfully. So I'm really happy to give a talk in this beautiful and a historic room like this. And so I wish my paper would live up to it, but probably not. So definitely my paper will not be beautiful, but there's some historic element to my paper. So that's the best I can do here. Anyway, so as Hakan mentioned, this paper is joint with York Stoy at Cornell. And so what we are doing here is basically, so this is the historic part. There's this line of research. It's a classic line of research initiated by McFadden and Richter. And so apparently this started in like 1960s. So obviously lots of you guys aren't born yet. So this is really has a long history. But the interesting thing is that, so they came up with this idea way back, and in the end, actually that paper, in a way, started modern microeconometrics. So it's such a historic paper, but on the other hand, for whatever the reason is, they never did a research about actually how to use their theory using data. So they came up with this beautiful, purely microeconomic theory, but indeed, it's fair to say there was no econometrics element to it. So exactly that's the kind of a gap we want to close, meaning that we want to show how to take the McFadden-Richter celebrated theory to data. So that's what we are doing. And so we're going to have some statistical discussion on the statistical method, and then we have some applications, some simulation results, and then I'm going to conclude. So that's the paper. Okay, so I'm going to just state the problem later. So as I said, this is based on this classic research by McFadden and Richter about so-called stochastic rationality. And at this point, you don't have to know exactly what they mean by stochastic rationality. But if you know the really basic microeconomics 101 type reviewed preference theory, that's enough. The rest I'm going to explain. And so this is what kind of I mentioned. And then, right, so it turns out that this problem, the approach we are taking is extremely computationally intensive. So how to compute our statistics and how to do inference, the computation is a huge issue. So I'm going to be talking about computational aspect of this procedure in detail, and then I'm going to talk about how to do a inference. So this is the econometrics part. Okay, and then I'm going to apply this to the some data using the UK data, and then I will talk also about how to do a kind of policy prediction, policy evaluation kind of stuff. And indeed, actually, probably this is even more interesting, just sort of taking the McFadden-Richter stuff to an econometric framework. But we are now turning the problem into a prediction problem. So this is very interesting, but unfortunately, this part is sort of still we are working on it. So I'm going to talk about it, but probably not much. Okay, and so, right, okay, so that was my introduction. So unfortunately, now I get into math a bit. But as I said before, it's very standard up to a certain point, at least. If you have any question at this point, please ask me because it shouldn't be technical at all. So if it sounded technical, then that's totally my fault. So you should ask a question. Okay. So this is something, at least in econometrics, called a random utility model. So if you really don't know anything about random utility model, actually at first you want to forget about this random part. So this is totally standard micro theory. So U is the each individual's utility function, and the problem is really simple. So price is P. So to just fix notation, I say that's k-dimensional, but it really doesn't matter. Now, so I say the budget set is indexed. Indexed by P. So you might think that okay. So at this point, so I just said price. Where did the income go? But what I'm doing here is just normalize income to 1. And when I say that, sometimes I get this question that, so you must be imposing some restriction, but I'm not. So this is just a normalization, meaning that if the budget constraint, so again, this is standard micro, so P times consumption has to be smaller or equal to income, and then I'm just dividing both sides of the inequality by the income level to make the right-hand side 1. So it's the definition of price that gets divided by the income level, and that's something I'm calling P now. So really, it's just a matter of making notation simple. Other than that, I'm not doing anything. So it's not like I'm not, assuming homogeneity or that kind of stuff at all. Okay. So each budget set is now indexed by P, and then each consumer maximizes the utility U over the budget set. And so this is, as I said before, this is the standard utility maximization program. So far nothing. But then, so I'm talking about random utility model. So now I say, oh, by the way, each person receives his or her own utility function, and so U varies from person to person. So that's the kind of a point of departure. And so I say here unobserved heterogeneity. So let me just talk a little bit of background of this kind of research. So in a standard, at least in microeconometrics, when typically people, introduce stochastic term, typical kind of interpretation is that say something like epsilon, that's representing each person's taste or stuff like that. So that's usually the term that represents unobserved heterogeneity. And sometimes people allow a little bit more complicated, richer space for the unobserved heterogeneity, meaning that sometimes people estimate, say, linear model, and people assume that in the linear model, the coefficients are all random, and so that's something called random coefficient model. So people do that too. So in that kind of case, the unobserved heterogeneity is multidimensional, but still it's a finite dimensional. So if it's like 8-dimensional regression, and then the heterogeneity is 8-dimensional. So here the difference is, so I say each person gets a function. So mathematically speaking, that means the dimension of the heterogeneity is actually it's an infinite dimensional space. And I actually put really, really little restriction about the dimension of heterogeneity, how the heterogeneity enters the model. All I'm assuming here is that each person gets his own utility function. Now, if I say that, you might think that, okay, so how do we proceed? Because we get data, but I'm telling you that each person's utility function is different. So what's the kind of empirical content of that kind of a model? So here, I don't write it here, but the fundamental kind of identification assumption for this research is that even though every person has a potentially different, random utility function, however, those utility functions are drawn from same one population. So in a way, to make the story sort of concrete, I can say that, okay, so suppose I have data for, say, 100 people, and then I say, well, I'm worried about the difference in the taste of people in, say, St. Petersburg. And then that's the population I'm looking at. And of course, typically, the population I'm targeting is a little bit larger, the whole Russia or whatever it is. But just to make the story simple, so I have this population of St. Petersburg, and then I'm taking a random draw of utility function out of that population. So that's the assumption or identification assumption I'm making here. So that even though I said this is a stochastic revealed preference theory, actually as you can see, there's absolutely nothing stochastic about this utility maximization part. This is really economics 101 part. So this is totally deterministic. Once I have utility function, your taste, and your budget, and then I know the answer. There's no randomness here. So it's not like there's uncertainty in the model. However, the econometrician doesn't know what U is. So that's the unobserved heterogeneity. Okay, so that's the setup. Oh, by the way, of course, if you have any question, during my talk, please interrupt me, because I don't want it's really a simple paper. It's just conceptually, it's very different from other kind of econometrics paper. So I don't want to confuse you just because of that. Okay, so that's the setup. So what does the econometrician observe? So basically what we observe, or say what I observe, is the pair of each person's consumption choice and the P, which determines your budget set, basically. Okay. Well, probably most precise statement is I observe the probability of people's choice within whatever this set A is. I know, given the budget set P, I know the proportion of people who are choosing his or her consumption within whatever the set A is. So that's what we know. And I'm very vague about what kind of the choice space, meaning that I didn't say that the choices are something like continuous, like how much non-durable goods I purchase. I didn't say that, so it can be discrete. It can be like whether you buy a car or not, or it can be continuous, like how much water I buy. But anyway, so it can be in both ways. So the question I'm asking, and actually question what McFadden and Richter asked, what I believe in 1960s, is this. So this is what, in general, we should be able to get this part out of your data. Of course, in practice, you have to estimate this thing, but if you have lots of data, and then you should be able to estimate this thing really precisely. It's just, you can just count the proportion of people whose consumption Y belongs to whatever the set A is. So this part is very easy. So let's assume that for the time being, we know exactly what this guy is. And then what McFadden and Richter asked is, suppose this is given, and then can the observed choice probability pattern, this guy, be rationalized, justified as a outcome of setup like this. So the setup is everybody gets utility function, and everybody solves this standard consumer maximization problem. So that's the question McFadden and Richter asked. So that's the main literature. So kind of surprisingly, they moved kind of slowly. So they started in 60s or something, and then they wrote some paper at some point. There's one paper in 1991, and kind of the definite final version came out in 2005. So if you are a student, you shouldn't take this approach. You come up with this idea and you finish your paper 45 years ago, which is not recommended. But people like McFadden can afford it, I guess. So anyway, so that's what happened. So if you are really interested in this kind of stuff, and then this McFadden paper in 2005 published in Economic Theory is a good resource. It's very technical, but everything is there. So what they call this whole theory or the concept the axiom of stochastic revealed preference, ASRP. So what Yoke and I want to do here is how to first test the axiom of stochastic revealed preference, but sometimes I say stochastic rationality, sometimes maybe something else, but it also refers to this. Okay, so, right. Now, so in terms of econometrics, of course there's a big literature of doing revealed preference analysis using econometrics. And probably the kind of an early classic example is this series of papers by Varian. So he wrote really back then how to take the theory of standard revealed preference to data. So the difference between what we are doing and what they are doing, especially like the say Varian paper, is that the Varian paper still assumes the standard non-stochastic revealed preference theory. So in his analysis, U is totally given, just one utility function. There's no, it's not representing unobserved heterogeneity. But of course, if you do that, everything is deterministic. And but of course there's some gap between the model and data. That is life. And so to fill that gap, what kind of all these papers do in a kind of maybe it's an unfair description of what they're doing, but in a way, they just throw in some epsilon between the model and data. And sometimes they call it like measurement error or whatever it is, random shock or whatever it is. So the model they're doing is totally non-deterministic revealed preference theory, whereas what we are doing is that uncertainty is brought up in a very formal upfront way. So for us, we can deal with certain measurement error, but uncertainty is coming from the fact that everybody is getting different utility function. The econometrician doesn't observe. So that's the fundamental difference. And in that way, what we are doing is a little bit more in line with a modern microeconometric research, where if you kind of throw in epsilon, sooner or later somebody asks, so what is that epsilon representing? And the best answer, well, the usual best answer is, well, that's representing unobserved heterogeneity, and we are able to say that because that's brought up front. So anyway, so there's a variant paper, and then there's this Epstein-Yachu paper, which is kind of in a way similar. And then there's this very important series of papers by Blundell, Browning, and Crawford. They carefully implement their stuff, and indeed the data set I'm using, we just borrowed from these people. But still, even though they are very careful about the interpretation of what uncertainty is, still basically the theory is standard revealed preference theory. Okay, so, right. And then there are a little bit more recent papers which is a little bit closer to what we are doing. So Blundell, Christensen, Matsking assumes some assumptions about the underlying demand functions property, and then throw in some term that's representing the unobserved heterogeneity. And so in a way, it's similar, but still the fundamental concept, let's say they have more assumptions than what we are doing. And then this Hodder Story paper is, in terms of the level of assumptions, it's very similar, but they're looking at a little bit more specialized case, whereas we are looking at very general case. The number of goods can be arbitrary, and so on and so forth. So there's this paper, and then so Lubell and Hodderline paper is more or less, in a way, it's they are looking at integrability condition basically. So the aggregate demand is whether it's consistent with a sort of random utility function setup. And then finally, this Maskey paper is in a way very close. When we turn the problem into the counterfactuals, basically the idea is the same. Once again, his setup, his Maskey is looking at very special case, but the idea is the same, and indeed, he's using the kind of all the programs we wrote because that's kind of close. So that's what's going on. Okay, so as I said before, I mainly talk about how to do testing. So whether the observed data sets are consistent with the McFadden and Richter stochastic utility function stuff. And then if I have time, I will talk how to do counterfactuals using the framework. Okay, so once again, I said this before, but the bottom line is that we really assume very, very little about the dimension of and form of unobserved heterogeneity. The form of utility function is totally general. So that's what's going on. Okay, so basic setup. I should watch the time. Okay, so I am going to focus on the case where there are only finite number of budgets, and indeed, when I show you the actual application, the number of budgets is actually 8 typically. So there aren't many number of budgets, partly because there's this computational limit. So already some of the matrices we have to deal with has like a dimension of 500,000, and I'm not making this up, really we are looking at matrices of enormous dimension. And every time we add extra number of budget, it kind of blows up. So probably the number of budgets here, capital J, is 8 or 9 at this point. Maybe can be a little bit better after a couple of years, but who knows? Okay, so there aren't just finite number of budgets. Of course, maybe in reality, actually, you might want to consider a continuum of budget, especially because I said, we have a individual income level, and of course, income level is continuous variables. So the budget sets, strictly speaking, varies continuously. So in principle, theoretically, and also in certain cases in practice, we should be able to do it, but I'm not going to do it here. So from the outset, the number of budgets we are going to focus on is just finite. But once I do that, and then, so I observe, say, 8 prices, P1, P2 to P8. So I have B of P1 to B of P8 budget, line or plane. And since that's a structure, it would be silly to just keep this notation. I just can call that I have first budget set, second budget set, budget number 8. So I'm going to use this notation B sub j. As I said before, the nature of your choices can be continuous or discrete, but there's a really neat trick here. So let me explain that part. Okay, so as I said before, this is what the econometrician observed. So y in A when budget set is bj. So and very important neat observation made by, I don't know who said that first, but at least it's in McFadden 2005 paper, is that, so I say blah blah here, but it's much easier to look at a picture, so here it is. So this is once again really standard, so the kind of revealed preference picture. So there are 2 goods, good 1, good 2. So the number of goods k is 2. And I forgot to mention, but in this setup, actually the number of goods is very unrestricted even in practice. So in application, I'm going to be showing we have just 3 goods, but we could have done higher dimension. That's not a problem. That doesn't complicate the computational problem. It's more the number of budget line here. That determines the computational complexity. But anyway, so this is standard, and actually I even don't need 3 lines. Let's just do 2. So let's just eliminate green here. So we have just blue line and blue budget set and red budget set. And so of course, in the standard revealed preference theory, you can choose all sorts of, when budget is blue, people can choose from here, actually here too. And when the budget constraint is red line, again, people can choose from here. One thing which you are not allowed to, and that's the theoretical restriction we would be exploiting, is of course, you cannot choose, say, this point and this point. That would totally violate the standard revealed preference framework that creates a cycle in your decisions. So that's not allowed. So, but the other side of this setup story is that that's actually enough, meaning that the theory really doesn't restrict the location within, say, this thing. So I call these things patches, just a name. And so the theory just tells you that if you choose a point when you're facing red budget, if you choose a point from this patch, and then if your budget line changes to the blue line, you cannot choose from this patch. So that's the restriction. But the theory really doesn't care whether you choose from here or here. So in terms of this constraint, actually it's enough to just count the number of choices for people who are on this budget line, whether when they are facing this red budget line, whether they chose this patch or this patch. But otherwise, you don't have to even record where each person was. So even though the actual data is actually continuous, and it is continuous in application, but when we do econometrics, you really don't have to do anything about continuous data. Actually, the data set automatically becomes discrete data sets. So suddenly the problem becomes sort of discrete choice, like multinomial choice problem. So it's not coming from, like, we assume some restriction. It's just straightforward application of the theory. But that helps us a lot because, as you know, dealing with discrete choice problem is, in a way, a lot easier than dealing with continuous choice problem. And so that's what I'm saying here. So I don't think I should really talk about notation, given that I already consumed 30 minutes. So you can just forget about what I'm writing here. All you have to remember is we automatically discretize our observation and turning the problem into a multinomial problem. Okay, and another thing at this point I should emphasize is that this paper is not about observing series of observations for one person, right? So since I said if somebody chooses their consumption from here, he or she cannot choose from choosing from here would be a violation. But the fundamental setup is that I only observe each person's choice once. So it's not like panel data or anything. So once again, so that's the kind of a most important part of the McFadden and Richter theory. They also assume that kind of setup. So one data set, one person, and I don't have a repeated observation. If I had a repeated observation, and then every time I see this choice and this choice for the same guy, and then I say, stop, that's a violation, revealed preference rejected, but that's not the setup. I observe one person only once. So that's that. And then, again, you shouldn't worry about the notation. What I'm doing here, however, is that, so remember that everything is now discretized. And so this J thing is representing the budget line. So in the previous picture, it was like red, green, and blue. So let's say J is red, and I represents each patch. So pi of I given J is just the frequency of people facing, say, red line, choosing, say, first patch, and then it's pi sub 1 given, did I say red? I said red? Red. And so on. And of course, that's I can go through patch number 1, number 2. So for example, in the previous picture, if there are 3 budgets on the red line, there are 3 patches, F and E and D. And so these I's just representing F and E and D. Okay. And so I observe the choice probabilities over, say, red budget and green budget and blue budget. So that's the data the econometrician observes, and then I'm just stacking all these given red budget. I stack all these choice probability into a vector. So once again, in the picture, this is a three-dimensional vector. And then, so these subscripts represent budget line. So this is blue, red, so on, and says J is green. And so I stack all these things. So even this vector pi can be fairly long. In application, I think it's something like 500 dimension. I don't quite remember. But it's fairly a long vector. In any event, so what econometrician observes out of data can be just represented by this long vector pi. It's just a sequence of choice probabilities. That's all. And so we start it, and we want to figure out whether that is consistent with the rationality hypothesis or not, while accounting totally flexible unobserved heterogeneity. So that's the project. Okay. So now, more silly notation. Once again, it makes no sense to go through all these notation to some extent. So what am I saying here? Well, so as I said, for each person gets a utility function. So say my utility, there's a pile of utility function here. I just grab one. So that's my utility. And given my utility, I might face red budget, blue budget, and green budget, and so on and so forth. And then, so for given utility function just I grabbed, so J still represents the color of the budget line. So say I face budget line red, and of course, because of the whole setup, by facing red budget and having one particular utility function, I should be able to say that, well, I'm going to choose particular patch out of the red line. Okay. So that's this guy. So this is a vector. So again, if there are three patches on the red line, well, I hope I'm not losing you. Is everybody with me? Absolutely, there's no technical things going on here. It's just a little bit too much notation, I agree. But if you have any confusion, let me know. Okay, so everybody with me? Good, okay. So I'm facing red budget, and then I say, given particular utility function U star, I choose, say, second patch. So in that case, this vector is 0, 1, 0. That's all. And then, of course, we have to think about red line, green line, and blue line. So once again, I stack vertically all these vectors. And so this is, again, a say 500 dimensional vector. But still, so it's a sequence of zeros and ones. So that's this A of U star thing. Okay. So now, so the whole point of doing this revealed preference thing is that, of course, I can randomly create choice patterns. So I can say that, well, given my utility function, out of red line, I choose second. Out of the blue line, I choose the third patch, so on and so forth. And I can just create this hypothetical pattern of zeros and ones. But then there are choice patterns that are not allowed, which is exactly what I said. So if for the first thing it's, say, 0, 1, and for the second, the budget line, if 1, 0, it's a violation. So I cannot have 0, 1, 1, 0 pattern. And that's exactly the restriction we would be focusing on. So that's what I'm saying here. So even though this, this is I, capital I, so this is a very rich space of the choice patterns, But still, some patterns are not allowed because of this reviewed preference. Standard reviewed preference theory. So certain patterns should not be here, and that's exactly what we're going to use. But still, after eliminating all patterns prohibited by the standard deterministic reviewed preference theory, there are a large number of patterns available. And that's the dimension that gets very big very quickly. So as I said before, in our application, some of the data set H becomes 500,000 and stuff like that. So this is a humongous vector, especially in terms of the, so I just collect all these valid choice patterns, and you can calculate, you will see these numbers when you run our program. And there are literally, 500,000 vectors sitting there on your computer, and remarkably, this computer will take that kind of thing.
So it's not a sparse matrix.
It is kind of sparse, actually. Right. So I will. Well,
Run out of memory.
Yeah. So probably there is a way to exploit sparseness a little bit more explicitly, which, not being a computer science guy, actually I don't. So we do some kind of a computational package to deal with high dimensionality, but actually we are not so sure about whether we are fully exploiting the sparseness of A, which is probably a good thing to do, and that's probably over our head. York is at Cornell, and Cornell is known for computer science. So our plan is, if we want to do a little bit more, probably I will talk to a real computation guy. But anyway, but I will come back to the computational stuff a bit in a minute. Okay, so there's this huge matrix A.
To interrupt, we have 10 more minutes for presentation, and then we will take some questions.
Oh, okay. Okay, I think I can do this. All right, so there's this matrix A. Okay, so.
Type is consumer type or type of budget?
Sorry?
So what type? What it stands for?
I'm sorry.
Type.
Type, yes.
Is it consumer type?
Yeah, so that's a good point. So as I said before, that's extremely important point. So you can probably at an intuitive level, we normally call them types, actually. So absolutely. However, strictly speaking, and then H is, even though it's 500,000, still it's a finite number. And then are we assuming there are, even though it's huge, finite number of types? And that's not true, meaning that the fundamentals are utility function. And so utility functions are, in a way, infinite dimensional. I don't know how to say it's continuously distributed, but it's not like H types. So when this H, the reason why it becomes, even though it's big number, it becomes finite number because of the finite dimensional nature of the theory. That makes it enough to consider finite number of choice patterns. If we didn't have the trick of converting the continuous choice problem into a finite, discrete choice problem, we couldn't do that if we original assumption is that U distribution is whatever. So it's really tightly linked, the trick of making everything discrete, and this thing becomes finite. But still, yes, the interpretation of the columns, they are types. So they are, 500,000 types of choice patterns exactly. Yes.
Do we have matrix A for every budget, possible budget?
So I already stacked the choice pattern for budget so that was the kind of notation I really went through really fast. So these are, each of them are vectors. So this is a choice pattern for red budget, green budget, so on and so forth. So yeah, so that's, but exactly, so lots of things are just pure notation thing. So I don't want to, you know, okay.
Is it correct that summation of components equal exactly
J? Wonderful. So I know you are with me. Okay, so all right. So that's how it goes. I'm sure everybody is with me. But anyway, okay. So but then so here's kind of what in a way McFadden and Richter said. So they said the choice pattern pi is consistent with rationality hypothesis if and only if this holds. So what is this thing? So A is the matrix of 500,000 choice patterns, and they are saying that if there exists a nu which lives in a h-1 the unit simplex, meaning that it's just fancy way of saying that this is like a probability vector. So this new vector sums up to, even though it's 500,000 dimensional long vector, it sums up to 1. Because exactly what you said, A's are like types. So it's like weighting different types. And after weighting different types, if you can reproduce the actual choice patterns, meaning choice probability patterns, and then the pi is consistent with the rationality hypothesis, and otherwise not. So that's the fundamental, and that's very intuitive. Hopefully, I think it's intuitive. So that's kind of what they say, and then also they say, well, there are different versions, totally equivalent versions of this. Okay, so it's 13 minutes, so I'll be quick. Different representation, just for simplicity, we choose to use this. Not that that's the only way to go. We could follow. I mean, we could take this hypothesis to the data. That could have been done. We are not just doing it. Okay. Once again, there's some math here. It's pretty simple. There's nothing fancy about it, but I'm going to skip it for the sake of time. So somehow the original hypothesis is that there's a probability vector nu that makes A times nu being equal to pi. But then, with some trivial math, I can claim that no, it's not even necessary to assume that nu sums up to 1. The only thing you have to assume, you have to impose is nu is, every element of nu is non-negative. So that's what I say here, which is kind of nice, because then, so after doing this thing, so this is a little bit of geometric stuff. So again, A's have a bunch of columns, and so A times nu is the weighted average of columns. Okay, so suppose, the fingers, each finger represents the column of A, because each is a vector. So there are lots of vectors in high dimensional sticking out, but here it's a 3-dimensional space, 3 vectors, because I can do 4, but that's hard, so 3. And so 3 vectors, and we are saying that pi can be represented as a positive linear combination of these vectors, meaning that all we are saying is that the observed choice pattern pi has to live in the space spanned by these three fingers, which is of course a cone, right? Hopefully you can see it. So it's a finite dimensional cone. So basically what you have to test is whether observed choice pattern is within the cone or not. That's the only thing you have to do. Therefore, as I do here, what I do is just calculate a minimum distance between the observed choice pattern and the cone. And this calculation goes really fast, even though the dimension of pi is even 500,000. So I think that's where somehow our program is using sparseness, because otherwise I don't believe it's so fast. But it does do a very good job. And so this part is actually very quick. Well, at least like wait 2 minutes and then it can be done. So that's nothing. So that's that. So that's basically what, in a way, that's the basic insight, because I at least theoretically knows where the observed choice probability pattern should be in this space. It should be inside of the cone. I calculate a minimum distance between the observed choice pattern and the cone. If there's a positive distance, well, that means it's outside of the cone, so you reject. And otherwise, it's accept. But of course, the problem here is that pi is estimated. So you have to take account of the uncertainty. So that's where the econometrics comes in. And so since I have 9 minutes, and probably I went through 20 slides and I have 70 slides or something, so I scroll hard ahead. And so let's see. But of course, in practice, what you do is you estimate pi using actual data, which is easy. It's just a choice frequency vector. So you can just calculate this, and then what you are going to do. So this is I didn't explain this too carefully, but this is basically calculating the minimum distance between the observed pi and the cone, right? So this is after this minimization, this is a minimum distance. And if this minimum distance is too big, and then you say, aha, the actual pi is outside of the cone, let's reject, otherwise you accept. But of course I said large, and the real question is what is large? So that's the hypothesis testing part.
When you calculate pi, you admit sampling error?
Yeah, you can, that's fine. Exactly. So measurement error can be allowed in the estimation of pi, exactly. Well, meaning that I can't do measurement error in prices. I think it's too hard. Especially, I only use 8 prices, and if I have measurement error, kind of you are screwed up anyway. So prices, I can't have measurement error. But choices, we can have certain measurement error. But the basic notion here is that the kind of a randomness comes from unobserved heterogeneity. Right?
Do you take into account sampling error?
Sorry?
Sampling error, do you take into account?
Sampling, yeah, that's inside of it. So you really don't have to distinguish the two, actually. Yes, so yes. Okay, so, right. So I'll just give you a picture of how you do it. Okay. So, picture. Okay. So as I said before, the only thing, and then I'll finish. Okay. So as I said before, you're testing whether the observed choice pattern is inside of cone like this. That's what you want to test. And literally, that's inside of your computer, right? And so suppose, so this part is a bit technical indeed. So this is a kind of a cut. Yeah, this is a technical part. But the upshot is that the problem here is that if the true, say, probability vector is that red dot, and then you have to use a special calculation to do critical value calculation, and people know how to do it. But the problem is that in reality, of course, you don't know where the red point is. If you know the red point and then the game is over, you can just tell the red point is inside of the cone or not. But something like this, as you can see, it's on the edge of the restriction, and so it gets technical or non-standard. And so the current research about kind of set identification inference, and these people say if that's the case, probably, so if the truth is here, then observed choice pattern is distributed somewhere around here. So suppose the, yeah, it's kind of getting too technical, I know, but say this is the estimated choice probability. And so when you do an inference, you have to impose null when you do hypothesis testing. I'm sorry, I know I'm not explaining exactly what but anyway. So the standard, say, bootstrap textbook would say, well, move here. This is the cone, move here, and then it's done. The problem is that it's not the right point. It's away from the truth. So you think, well, maybe it's around here, and do bootstrap, and then because it's qualitatively at a different location, you get the wrong answer. So what the current research says typically is, well, then when this distance is short, move there and bootstrap from here. So that's what they say. The problem here is that everything is like a million dimension. Actually, we never know where the cusps of these cones are. And so that's a problem. And if I can calculate exactly where these the cusps of the cone, and then it's very easy given the current literature, but we can't do it. So the upshot here is you have to do something else, which what we are calling a tightening track, and so we just tighten stuff and it works out. I just want to show the outcome. Okay, so true budget lines look like this, and so theorems, lots of theorems, and so here's one outcome. So for certain data set, this is the kind of the distribution kind of a critical values, and the test statistic itself is 0.23. So of course that's an overwhelming acceptance. Interestingly, all the observed choice pattern pi hat is actually out of the cone almost every time, which we didn't know. But so still you have to do a testing to figure out whether the difference is significant or not. In this case, obviously non-significant, but sorry. In this case, actually, the test statistic is 2.58. So p-value, according to this, is 10%. It's still acceptance, but this is a very subtle case. You really have to do a real inference. So that happens. Okay, so then you can do prediction, which is very interesting, but you have to read my paper if you are interested in. So in conclusion, so we developed an empirical test of stochastic rationality, lots of computational stuff, and the inference methods are complicated, but we made it very easy, and you can turn things into a prediction program, which is our next step. So I stop here.
Thank you very much.
Okay, thank you.